Let's look at an example today. So let's say there are two anti-parallel current-carrying wires as shown in the figure. The currents flowing through both wires are each 10 amps. Using the distances provided, calculate the magnitude and direction of the net magnetic field at points A, B, and C. Okay, so important things that we have to know is this equation right here. So this is the equation for the magnetic field produced by a straight wire, as these are. And also you have to be familiar with the right-hand rule. So real quick, if you use your right hand, you can see that in this top part right here, your thumb is in the direction of the current I, and your fingers will curl around in the direction of the magnetic field. So to the right of this wire, the magnetic field is going in, and on the left is right here, the magnetic field is coming out towards you. Okay, so with that in mind, let's start at point A. So let's calculate B net A. Okay, and as we can see by, let's call this wire 1 and this wire 2, if we use the right-hand rule for wire 1, we can see that the magnetic field is coming out. So say B1, and for wire 2, we can see that the magnetic field is going in, so it's B2. And now, without doing any math, if we think about this conceptually, from our equation, we see that B is inversely proportional to R, the distance. So because wire 2 is really far away from point A, it has a large distance and a small magnetic field. So B2 is going to be less than B1 because the distance from wire 1 to point A is much closer, much smaller, meaning that B1 is greater. So the direction of the net magnetic field at point A is going to be in the direction of B1. So if B1 is coming out, that's going to be the net magnetic field. So let's solve this. Let's say it's B1 minus B2. And again, the reason why I'm doing B1 minus B2 is because B1 is stronger. It's going to win if you were to say that. So let's plug our values in. Mu naught is just a constant. So mu naught equals 4 pi times 10 to the negative 7th, just a constant, times I. So for B1, I1 is 10 amps, which is also I2, divided by 2 pi times R. So R1 in this case is going to be the distance x, and right here we see that x is just 5 meters, like that. So this is 4 pi times 10 to the negative 7th times 10 divided by 2 times 5 is 10, and we still have the pi. So there's a lot that cancels here. So B1 is 4 times 10 to the negative 7th. Okay, and then let's subtract B2. So we still have the constant times 10 divided by 2 pi, and then now R2. So R2, the distance from wire 2 to point A, it's going to be this x plus this x. Okay, so in that case it's 2x, or 10. Okay, so we have 4 pi times 10 to the negative 7th divided by 2 pi. So if we keep canceling, we get this. And we finally get that B net at point A is going to be 2 times 10 to the negative 7th Teslas. So that's our answer for point A. And to also give you the direction, like we said earlier, just from the conceptual part of it, it's that B1 is greater than B2. So if B1 is coming out, then the direction is out of the page. Okay? And now let's keep doing the same thing. Let's figure out what it is at point B. So if we use our right hand rule for wire 1, we see that our thumb is pointing upward and our fingers are directed into the page. That's B1. And let's use a different color. If we look at wire 2, using our thumb going down, our fingers will wrap around in as well. Okay? So now, point B is midway between these two wires. So that tells us, yeah, let's write this. So B net, point B, is going to equal, because they're both going into the page, we're going to add them this time. B1 plus B2. Okay? And the distances, R1 and R2, they're both the same distance away because it's the midpoint between the two wires. So it's just going to be 1/2 x, okay, which is 2.5 meters. Okay, so let's start to solve this. We're going to use our same equation, 4 pi times 10 to the negative 7th times the current, 10 amps, divided by 2 pi r. So that's 2.5. And because, they're the same distance away and the current is the same, B1 and B2 are going to be the same value. So let's just multiply by 2 instead of adding them together. So let's see what our calculator tells us after typing this in. So 4 pi times 10 to the negative 7th times 10 times 2 divided by 2 pi times 2.5. So here I get 1.6 times, let's see, 1, 2, 3, 4, 5, 6, times 10 to the negative 6 Teslas. Okay, and so that gives us the magnitude of the net magnetic field at point B. And after using our right-hand rule to draw what is actually happening, we can see that the direction is into the page. So let's write that. Directed into the page. Okay. And lastly, let's work on point C. So B net C equals, and again, just looking at this conceptually, we can see that wire 2 is closer to point C than wire 1 is. So the strength of the field produced by wire 2 is going to be greater than the strength of the field produced by wire 1. So in that case, B2 is going to be stronger than B1. Okay, so we're going to do B2 minus B1. So 4 pi times 10 to the negative 7th times 10 amps divided by 2 pi times the distance. So how far away is wire 2 from point C? We see that it's 2x, okay? And if x is 5 meters, 2x is 10 meters, okay? So this will cancel. 2 times 10 to the negative 7th, okay? Minus B1. So 4 pi times 10 to the negative 7th times the 10 amps divided by 2 pi times the distance from wire 1 to C. So wire 1 is this 2x plus this x, so 3x, so times 15 times 15 meters. Okay? So let's see what our calculator gives us. We have 2 times 10 to the negative 7th minus, let's see what this value is, 4 pi times 10 to the negative 7th times 10. Okay, divided by 2 pi times 15. Okay, so I get a pretty small value, get 1.33 times, let's see, 3, 4, 5, 6, 7, 10 to the negative 7th. Okay, so 2 minus 1.33 is going to be 0.67 times 10 to the negative 7th Teslas. Okay, so that is our answer. That is the strength of the net magnetic field at point C. And for the direction of it, because wire 2 is closer and stronger, if we use our right hand rule, we see that B2 is coming out of the page. And if we do the same thing, we look at how B1 is directed, we see that it's going into the page. So the net direction is out of the page. Okay, so we found the direction and the magnitude of the net magnetic field at points A, B, and C. So thank you for watching.